Okay, first things first. Every solid engineering design begins with a crystal clear understanding of the problem and all the parameters we're working with.
Here's what we've been given. We've got the loads coming down from the column, both the permanent dead load and the variable live load. There are also moments trying to twist the foundation. The ground itself can only handle 200 kilopascals of pressure. Now the footing we're checking is 3.5 by 2.5 meters, with a thickness of 600 millimeters. And a really key number here is the effective depth, D, which is 530 millimeters. That's the distance from the top down to where our steel reinforcement sits. Our mission is to verify if this footing is safe and to specify all the required steel.
All right, our very first and honestly most important safety check is for punching shear. This isn't a failure you want to mess with. It's sudden and catastrophic, so we have to be absolutely sure our design can handle it.
Before we even touch a calculator, let's get a mental picture of what's happening. Imagine the column's concentrated load pushing straight down, hard. At the same time, the soil is pushing up all around it. If that concrete footing isn't thick or strong enough, the column could literally punch a hole right through it. Our job is to make sure that never, ever happens.
You know, the core principle behind any safe structural design is actually pretty simple. The strength of what you build has to be greater than or equal to the forces acting on it. Here, we call that design capacity versus ultimate shear. We use safety factors on both sides of this equation. We increase the loads to get the ultimate force, and we reduce the material strength to get the design capacity. It's all about building in a healthy margin of safety.
So first, let's calculate the demand, which we call VU. We start by applying factors to our loads, usually something like 1.25 for dead loads and 1.5 for live loads. This gives us a factored upward pressure from the soil. Then we calculate the total upward force acting on the footing. But, and this is key, we subtract the force acting directly under the column's critical area. What's left is the ultimate shear force the concrete has to resist, which in our case is 1798 kilonewton.
Now, let's figure out the footing's inherent strength, or its capacity, which we call 5VC. The building code gives us a formula for this. It depends on the concrete strength, or F'(C), the critical perimeter around the column, BO, and that effective depth, D. For this design, our critical perimeter is 3,720 millimeters. We also apply that strength reduction factor, phi, which is 0.75 for shear. It's just another layer of safety. When we plug in all our numbers, we get a design capacity of 2464.5 kilonewtons.
And here's the moment of truth. We compare the two. Our capacity is over 2,400 kilonewtons, while the demand is just under 1,800. So capacity is significantly greater than demand. That's a pass. The footing is safe from punching shear failure. Great. With punching shear out of the way, we can move on to the next potential failure mode, one-way shear, which we often call beam shear. For this check, I want you to think of the footing as a really, really wide cantilever beam that's sticking out from the face of the column. We need to make sure it's strong enough to resist a shear crack that could form at the most critical spot, which the code tells us is at a distance d away from the column.
So, just like before, we need to find the ultimate shear, VU. We look at that critical section, 530 millimeters from the column face, and we calculate the total upward force from the soil on the part of the footing beyond that section. That calculation gives us an ultimate shear force of 567.5 kilonewtons.
Now for the capacity. Take a close look at the formula here. You might notice it's a little different from the one for punching shear. It's actually less conservative, and there's a good reason for that. Beam shear is a more ductile, less sudden failure. So we use our concrete strength, the footing width, and our effective depth, along with that same phi factor of 0.75, and we get a design capacity of 828.13 kilonewtons.
And the final comparison is clear. A capacity of over 828 kilonewtons easily handles the demand of about 568. So that's another check passed. Our 600 millimeter footing thickness is officially adequate for both types of shear. Awesome. We've confirmed our footing is thick enough that it won't fail in shear. Now we get to the really fun part. Figuring out exactly how much steel reinforcement, or rebar, we need to handle all the bending forces. Let's start with the long direction. The first step is to calculate the ultimate bending moment right at the face of the column. That comes out to 657.2 kilonewton meters. We then plug that value into a design formula to solve for something called the steel ratio, which we call rho. It's just the ratio of steel area to concrete area. For us, that's 0.00254. Multiplying that by the cross-section gives us a required steel area of 1346 square millimeters for every meter of the footing's width. The practical solution? We'll use 7 16-millimeter diameter bars per meter.
Now, we just rinse and repeat for the short direction. The bending moment here is actually a little higher, at 719.25 kilonewton meters. We run through the same process, and we get a required steel area of 1,060 square millimeters.
Now, you might be thinking, wait, the moment is higher, but the required steel area seems lower than the per meter value before. That's a great catch, and it's because this calculation is for the total steel needed across the entire 3.5 meter length, not per meter.
Okay, we know how much steel we need in each direction, but that's only half the battle. The next crucial step is detailing, figuring out exactly where to place all this rebar.
See, with a rectangular footing like ours, the bending stresses aren't uniform. They're much higher right in the middle, under the column. The design codes are smart about this. They tell us, hey, you need to concentrate a bigger chunk of your short direction steel in a central band. The big question is, how much more?
Well, luckily, the code gives us a simple formula to figure this out. It's all based on the footing's aspect ratio, which we call beta. For us, beta is just the long side divided by the short side, so 3.5 divided by 2.5, which gives us 1.4. We plug that number into the formula, 2 divided by beta plus 1. The result is 0.83.
So what does that 0.83 mean? It's simple. It means that a whopping 83% of our total short direction steel has to be concentrated in a central band. The width of that band is equal to the footing's short dimension, so 2.5 meters. The rest of the steel, that leftover 17%, gets distributed evenly in the two outer zones.
And there we have it. This table puts it all together. Our final design summary. The 3.5 by 2.5 meter footing with a 600 millimeter thickness is safe for shear. The long direction needs 7 16 millimeter bars per meter. And for the short direction, out of the total 10.1 square centimeters of steel we need, 8.6 of that has to be placed in that central 2.5 meter band.